Here in Lesson 7.3, we move on to another type of hypothesis test for a mean. The one we learned about in Lesson 7.2 was when the standard deviation of the population was known. In this lesson, 7.3, we're learning about the type of hypothesis test we do for a mean when the standard deviation of the population is not known. So hence we're going to be back into our t distributions that we used in chapter 6. So our targets in this lesson are, 1, to be able to find what are called critical values in the t distribution. And in MyLabs Plus, they use the notation t sub 0. 2, use a t-test to test a mean when sigma is not known. And then 3rd, and I won't get into this in the video, but it is on the slides I printed for you, how you can use technology to find p-values for those of you who have the graphing calculator, and then use those p-values with a t-test for a mean, mu. So as always, there's a process that we're going to follow when we conduct one of these hypothesis tests. First, identify the level of significance, and we know that we use the symbol alpha for that, and it's typically given to us. Second, identify the degrees of freedom for that hypothesis test, which, like confidence intervals, is going to be the sample size n minus 1. Third, use our table 5 that we have for t distributions and find the appropriate critical value. Okay, that appropriate critical value is either going to be one that we obtain if we have a left-tailed test, a right-tailed test, or a two-tailed test. So if it's a left-tailed test, and we'll demonstrate this, we'll need to go to the column that's labeled 1 tail alpha and then find the appropriate critical value, but we'll need to attach a negative sign to it because we will be below the claimed mean. If it is a right-tailed test, we'll go to our table 5 and find the 1 tail alpha row at the top with the appropriate degrees of freedom and find the critical value, and this one will have a positive sign because it will be above the claimed mean. The third type would be a two-tailed test. So now we have to go to the row at the top of our table 5 that has 2 tails alpha. Find the appropriate value, whether it be 0.20, 0.10, 0.05, 0.02, or 0.01, and then we'll have 2 critical values, one that has a negative sign and one that has a positive sign. So let's practice. Hopefully you have your table 5 in front of you. Find the critical value, and the formatting just didn't come through okay, t sub 0 for a left-tailed test given an alpha of 0.05 and a sample size of 21. So first, my degrees of freedom is going to be 21 minus 1, which is 20. My alpha level is 0.05, and it is a one-tailed test, in this case left-tailed, which means we're going to get a negative critical value. So if you look in your table, you go to the row labeled 1 tail alpha at the top, find the alpha level 0.05, the second column, go down to degrees of freedom equal to 20, you should see a critical value there of 1.725. But because we're doing a left-tailed test, that means that our sample average will be below the mean, then our critical value will be negative, as pictured in that drawing, okay? So in the null, we would have said that mu equals something, and that's at the center of our t distribution. If our sample average ends up in that tail there that's shaded in blue, out beyond a critical value of negative 1.725, then we will reject the null hypothesis. Find the critical values t sub 0 and negative t sub 0 for a two-tailed test with a level of significance alpha equal to 0.10, and sample size is 26. So again, our degrees of freedom will be one less than 26, which would be 25. So this time we have to go to table 5, find the two tails alpha row at the top, go over to the second column where you see a 0.10, and then down to our degrees of freedom of 25, and you should see a critical value of 1.708. But because this is two-tailed, that means we're going to have a positive and a negative critical value. So if you look at the t-distribution pictured here, you should see that if you go 1.7 standard deviations below the mean, or claimed mean, which would be at the center of the curve, you have a tail shaded in blue whose area is half of alpha, 0.10, which is 0.05. If our test statistic ends up in that blue shaded region, we will reject the null. But we also might end up with a mean that's in the blue shaded region in the right tail, which is 1.708 standard deviations above the claimed mean. And so if our test statistic ends up in that tail, we will also reject the null. That tail also has an area of 0.05, so the two tails together have a total area equal to alpha, which in this case is 0.10. So here's the process we're going to be following when we go about calculating or conducting a hypothesis test for a mean when the standard deviation of the population is not known. First, we want to be sure that it is reasonable to use this test, and so we need to have a population that is normally distributed, or we know and needs to be large, and we know from our confidence intervals that large is at least 30. Okay, then we'll calculate a test statistic, okay, for our sample average x bar. And I want you to notice that when you compare this formula for the test statistic, it looks much like the formula for the test statistic for a z-test. The difference is the formula we learned for a z-test has a standard error in the bottom of sigma divided by root n. Well, we don't know sigma here, and that's why we're in a t-distribution, so we're having to use s in its place. So the formula is very similar, it's just that we're using s instead of sigma. Our degrees of freedom, as we said, will be S1. Okay? So, step 1, verify that sigma is not known and that the sample is random, and either that the population is normal or that n is large, greater than or equal to 30. Second, state the claim mathematically and verbally. Identify the null and alternative. The claim may be in the null, it may be in the alternative. We'll have to see based upon the wording of the question. Third, specify our level of significance we know is alpha. Well, that doesn't look like alpha. Okay, that'll be given to us. Fourth, identify our degrees of freedom, which of course is n minus 1. Fifth, find our critical value using the table, and I see on my slide I say table 4, it's actually table 5. Seventh, find the standardized test statistic by using that formula we addressed previously. Eighth, make a decision now. Is our test statistic in the critical region or not? And then we will either reject or not reject. And then last, identify what that decision means in the context of the original claim.